Okay, so we're just going to continue. So we had done the question number 4, except like question number 4 has an extra part where you want to find the Q and W for a process from A to B along the curve given by this thing p equal to 10 power 5 plus 10 power 9 times v minus 0.02 to the power of 2. So just going to integrate, obviously. So just integration of negative PD. So we want the work done on the on the, what do we call it, on the system. So it's just negative integration of pdv. So just this quantity, which I'm just gonna do it like directly, sort of. So just 10 power 5 times v and plus 10 power 9, so q upon 3, right, upon 3. So just some substitution, whatever. So v minus 0.02 to the power of 3, yeah. And this is going from v equal to 0.01 all the way till 0.03. Cool. And we are in fact going you know, from what to what again, from a to b, right? So this is the thing. Cool. Which is like what, so just going to plug stuff in. So it's minus of 10 power 5 times this stuff, so it's 0.02. That's gonna be 10 power 3 times 2 plus this thing 10 power 9 upon 3 times, so the cube of that, the right. So it's 0.03 minus 0.01 cubed, so that's going to be 10 power negative 2 cubed. That's 10 power negative 6 minus, just put negative of that, so just you know, right, plus in fact over there, so just negative of that, and that's why this is plus. Just put that over there, you just get like 10 power negative 6. Cool. And so this combined is 2/3 of 10 power 3. Yeah, so this just becomes negative. 6 plus 2 is like what, 8. 8/3 of 10 power 3. It's cool. Now we know that the energy change, the total energy change was just for the A to B process was just 2500, right? Does this sort of match? I guess so. It's 2000 upon 3, so whatever. So that's the work done on the gas. It's negative of all of that. So just like write it down. So W is just minus 2 by 3 times 10 power 3. So 2000 upon 3 if you prefer, which we can sort of approximate, which is like, okay, so we need 18, so just minus 6 and then 20 again, so 6 again and then 6 again and 0.6, so on, so 6.7 approximately joules, obviously. So 6.67 joules. Delete all of that and say negative, obviously, because the work done on this is negative since volume is increasing. Yeah. So the heat given to this, that's just its delta E minus the work done, which is, so for A to B it's to 2500, so 2500 minus of this guy. So just do this to 2500 plus essentially 666. There's only 3 of these guys. Okay, 666.67 whatever, which just happens to be 3 1. I mean, why am I doing this thing? Just 3166.67. Yeah. Cool. So this is question 4. Question 5 is the energy of a particular system of 1 mole is given by U equal to AP square V, where A is some constant. You want to find the equation of the adiabatic in PV plane. So this is pretty obvious. You know that du is just TdS minus PdV. Well, you want ds to be 0. That's essentially the thing. So now just du is A times, so 2A PV dP and plus AP square dV. That's equal to minus PdV. Cool. So from here just like integrate, right? So this goes over there, so just get plus, so the dV terms calculate, so like dV times of AP square plus P, and then from here you just have something with dV, so plus 2APV dP is equal to 0. So yeah, just put this over there and then this over there, so this cancels, it just becomes AP plus 1, right? So integrate that, just get like natural log of beta upon V1 plus plus this whole thing is just 2A natural log of AP plus, so yeah, that A you can actually use basically. It's just like 2 natural log of ap2 plus 1 upon ap1 plus 1, and that's equal to 0. That's essentially the thing. So what we are saying is that v times of ap plus 1 squared is some sort of constant. That's the thing. So this equation and ds equal to 0, that implies this. Alright, question 6. Question 6 is 3 cylinders of identical cross section areas. So there's a figure given. I'm just going to draw this. So you have 3 cylinders. You have this fulcrum sort of. All these 3 cylinders are like fixed to the ground, and the ground is diathermic. That's what the question reads. The 3 pieces are connected to the rigid bar hinged on a, so this is a rigid bar, right? Hinged from the fulcrum as the ratio of 1:2:3. The cylinders rest on heat conductive table of negligible mass. The table makes no contribution to the physics of the problem. So I don't know why they told it's negligible mass. Like, what? I don't quite get what's going on. The table makes no contribution. Okay. I still don't get what exactly happened over here. Rest on a heat conductive table, right? So we can't just assume that the table itself is moving or anything, I suppose. The table makes no why did they say the table has no mass? Like, how does that even matter, right? Yeah, I don't quite get it. Why would that matter? So it said the table doesn't have any mass. The table makes no contribution to the physics of the problem except to ensure that the 3 cylinders are in diathermic contact. The entire system is isolated and no pressure acts on the external surfaces of the pistons. Okay, find the ratio of pressures and of temperatures in the 3 cylinders. I don't quite get the thing, but okay. So this is a fulcrum, so it's like pretty obvious. So by the way, also it's given that this is 1, this is 3. So if this is P2 pressure, this is P1 pressure, this is P3 pressure, right? This is actually labeled as number 2, this is labeled as number 1, and this is labeled as number 3. So what we kind of have is that 2P2 plus P1 is equal to 3P3. Other than that, there's nothing else that you can actually say, right? Sorry. Yeah, I don't think there's anything else you can say. Table makes no contribution. How does the table even matter in the end? It's not that the table itself can move, right? Unless it can't move, it doesn't matter if it's negligible mass or whatever the hell. What if it can move? Nah, that would be stupid. I don't think that's the thing. What about gravity? Oh, forget gravity. Just talk about pistons and pressure and that stuff. Yeah. And they want the ratio of the pressures. But how? Like, why the hell is just... I don't know. Okay, nothing is much is given, so I'm just gonna move on. Question 7 is find the equations. So the 3 equations of state for a system with the fundamental equation. So energy is given as a function of S, N, and V. It's this quantity. My God, what is this? Okay, what is theta? I don't know. What is R? I don't know. This is whatever this is. Just assume it's constant, I suppose. So yeah, let's just say this whole thing is just some constant alpha. So just have E equal to alpha S cube upon NV. Cool. Notice that if S is raised, so like increased by factor lambda, N is increased by factor lambda, and V is also increased by factor lambda, it seems that energy is also increased by factor lambda. So essentially what you have is that energy is still an extensive variable. So you can still sort of say that E equal to Ts plus, so minus p times of v plus mu n. I mean, okay, that is kind of obvious because that's just the definition of mu basically. Okay, so that's not what we want. What we want is these three variables. We want temperature, pressure, and chemical potential as functions of S, N, and V. Well, this should be easy. So temperature is just the derivative of energy with respect to entropy, right? So that's just like this thing, 3s square upon nv, so at constant volume. There you go. That was easy. uh, Pressure is just the negative derivative. Is it negative? No, the positive derivative. Wait. Okay, no. Pressure, negative pressure is the generalized force. So it has to be positive, right? Right. So, right, okay. Pressure is the negative derivative of energy with respect to volume. So P is just negative of, we'll just do this thing. So just negative s cube upon nv square. That's it. In fact, just s cube upon nv square. That's your pressure. The chemical potential is the change in energy with respect to the, oh, who am I kidding? If you want the mu thing, we should just minus TDS plus PdV. Yeah. So I know it's just a change in energy with respect to number of moles, number of particles, but something just doesn't feel right. I mean, we kind of know that E is equal to Ts minus PV plus mu n, right? Sorry, plus, I suppose. No, was it plus or was it minus? Okay, so this messed up. So it's h is just u plus b minus ts, right? So this is supposed to be minus of it. Minus pv plus mu times of n, right? So essentially we're saying like mu is just e minus ts plus. So yeah, that's probably a better way of doing it than. Usually mu is just the change it gives energy, right? With respect to n. Okay. Like, what does this even give us though? So you want the s and v terms to be constant, and then so I mean, okay, then it's like, okay, fine. I guess that's just the way it is. Fine. So you can use this equation, I suppose. So mu is just the derivative of E with respect to n at constant entropy and volume. Right, and that just happens to be, well, easy in this particular case. So yeah, just that, just minus s cube upon n square v. There you go. These are our quantities, right? So dp mu is just these, obviously. Cool. And just move on. Alright, cool. Question 8. Question 8 is, it's pretty big, isn't it? Oh, it's given a star. Okay, it's a hard question. Fine. So we'll go to that later. Let's go to some easier question. Question 10 looks easy. It's a lot less over there. So question 10 we'll just do first. Question 10 is, using Maxwell's relation, show that KT is equal to KS plus TV alpha square. Okay, I thought it was easy. It's not. Fine, just do it. Just do it. Where KS is minus 1 by V partial V by partial P, constant entropy. KT thing, what the hell? Okay, yeah, okay, that's fine. Maxwell's relations again. Wait, why do I feel we have actually shown this somewhere? Yeah, it feels like we've done this before, haven't we? So there's this alpha square CP stuff. So CP is just the, okay, I get that, but what's alpha square? Okay, what is alpha again? I guess it was somewhere, it was defined somewhere before. Right, okay, so alpha is the expansivity, so it's given as, so KT is the compressibility, fine. Alpha is given as 1 upon V partial V by partial T at constant pressure, right? That's cool. And then Cp is obviously just you know, yeah, so the rate of change of energy just will be that, right? So it's just that it's just TdS. So now it's like, okay, partial S by partial T at constant pressure. Cool. Right, so you have alpha square. This is very yeah, this looks so much familiar to something else we have done. Is this just coincidence? No, it's not. Oh, so we already proved this thing, that Cp minus Cv is oh, this is okay. They're just cheating. They're just putting more and more, what do we call this thing, similar equations. Fine, so we have already proved this thing. Wow, yeah, so there's only a few terms that are interchanged. So essentially you just have Cp is equal to Cv plus this stuff, right? Right, so now if you just switch Cp and, right, so if you multiply by Kt and divide by Cp, what you would have is this exact thing. So Kt would just be equal to Kt times Cv upon Cp upon Cp over there. And so now the only thing is these two terms should match. So essentially what you're saying is that Cpks is equal to Kt Cv, right? Let's just do this thing. So what is so I'm just gonna like bring down these equations as well, so copy them. So this is all you're really saying. Okay, this shouldn't be that complicated. So essentially, it's what you're saying is like partial V by partial P at constant entropy, that's Ks. Cp thing is just partial S by partial T at constant pressure is equal to, so just partial V by partial P at constant temperature, and then partial. Okay, so this K thing is also just V upon P, it seems, and it only has like adiabatic and isothermal things. Over here the Kt that we are using is isothermal. Oh, it's isothermal, it has to be. So this alpha P thing, that's at you know, constant pressure. Over here this is it at constant pressure? It just returns alpha. I don't know what to make of it. I suppose it's at constant pressure. Fine, let's just see if this works out, and we can just say it's constant pressure. Yeah. So Cv is just partial S by partial V at constant volume. Okay, so now once again we need to sort of change this, right? Yeah, so talk about constant pressure. So we can also write it like this thing, constant volume, and then partial V by partial P, sorry, at this thing, right? Okay, constant what? Constant heck, I think I have a better thing I can directly do. Also this should be a temperature thing, sorry. Yeah, right. Yes, that T thing just gets cancelled in any case, and it should be constant volume. So now think, what can you do? Well, you can probably write everything using just entropy. Right, that would make much more sense at constant entropy, right? No, wait, but you don't want that. So look, this is at constant pressure. You can convert that to temperature, but that's not going to be useful in the end. Okay, this I can convert at constant pressure again. That's just going to be derivative of that with CO2. Yeah, right. I certainly can do it. Why does this look so convoluted? Like, why is this like that? Like, whatever this is. Okay, so this I can convert to constant volume or constant temperature. There show you some better way than this thing, right? Partial P by partial V. I have seen that term before, right? Yes, I guess. No, wait, because that is the PV term, right? So, oh come on, think about it. No, it's impossible for P and V to occur together, right? Yeah, I mean, yeah, it doesn't make sense. So we want a temperature term or something. Okay, let's try to modify this then. So partial T can be written as set under constant pressure. We'll just say this is volume over there. We just have partial P by partial T at constant pressure. Right. I don't think this is really helping us. Okay. Fine. What else? The partial V by partial P thing. I don't have any bright ideas right now. Yeah, this too we should probably be changing, right? Constant entropy. Interesting. Constant entropy, you say? Have I seen this term? No, I have not. Okay, this should be partial V by partial T, basically, at constant entropy. This thing, yeah. I'm gonna need much more space, so copy that. No, I should probably not write it like that. I should simply just write partial S by partial T at constant pressure. Okay, that's what we want to prove. Now let's get to it. So we need to modify a lot of things now so that we can use the Maxwell's relations. So this just becomes partial V by partial T at constant entropy, partial T by partial P at constant entropy, then partial S by partial T at partial V at constant pressure, and then partial V by partial T at constant pressure. That's equal to partial V by partial T at constant temperature. That is weird. Okay, this shouldn't be the case. Okay, at constant entropy at constant temperature, and then partial S by partial P at constant temperature, partial S by partial P at constant volume, partial P by partial T at constant volume. Okay, this is stuff that you can probably deal with. Okay, so now this is done. We need the Maxwell's equations to be able to do stuff, right? Yeah. So where do we start as such? I guess probably by collecting terms. So let's just try to bring everything in, like just some few variables. So all of this stuff that's in S, I don't want that. I want it in, so this I want in T, this I want in P. Okay, P already is there. It's not good. Partial T by partial P, right? Okay. So okay, this is in P. This can also be written in P, right? Yeah. This can be converted to T. This can be converted to P. This thing can be, so both of these can be converted to T. I'm just gonna highlight a few things though. So these two are alike in a way. Yes. These two are alike in some way, I suppose. And this I can convert. Okay, and what about this one? This is pressure volume. This is volume and pressure. So these you will have to convert, sort of. Oh, I guess I'm just guessing. Think about it. This and that. Okay, no, don't get any hopes up. I don't think it's going to be that easy. So that's under constant entropy. This is under constant. Okay, that's not very optimistic, but whatever. So first we'll just try out the Maxwell's relations and see what happens. So you know that we just get like partially by partial x, partial s by partial y, minus, so PdV, so just partial P by partial X, partial V by partial Y, and that's equal to okay, this is the thing. Now we want some equivalence between these, so we want it in terms of okay, in terms of entropy and pressure, it seems. I really don't know what we are doing right now. Let's just do this then. Let's just see what happens. Okay, let's just like put something and just, you know. Why is this so complicated? Come on, just think. So this you can convert to pressure, this you can convert to pressure, and that will hopefully give us something. So we want stuff that has entropy and pressure in it, right? Okay, let's go. So just put X equal to entropy and P and Y equal to pressure, and let's hope we get something nice. So let's get partial T by partial. Oh, this is gone already. This term is 0, then minus this guy. So partial P by partial X, partial V by partial Y, right? So partial P by partial S, essentially. Oh, it's gonna be that long one, isn't it? Yeah. Right. That's a hard one. Okay, that's not the one that we kind of want. We can always change this stuff if you like wish. Oh, come on, there must be some way. To convert everything, right? So what variable is common everywhere? That's kind of the question you should be asking. I mean, this is kind of stupid. We just went from this simple looking thing to this complicated looking thing. The only reason is like we can now apply Maxwell's relations. But even then we kind of don't know where can we apply Maxwell's. So let's just go for the 4 Maxwell's relations which are easier to comprehend, and maybe that will give us something. Okay. So let's see. How do we get those? Well, 2 of these terms should cancel, right? So let's just start with X equal to P and Y equal to B, the usual thing. That's not good because it's going to give us a 1 term over there, so we cannot do that. So X equal to P, Y equal to T, how about that? Okay, that's sort of nice. So doing that, what do we get? We just get okay, this is gonna die. And what about this one? Partial P, partial, that's 1. So just negative partial V upon partial T at constant pressure, that's equal to, so X is P, Y is T, so this is 1, so just partial S by partial P at constant temperature. Cool. Now why can we use this? We can only use this if we have a constant pressure term or a constant temperature term, right? Partial S by partial P, that's okay. I spotted 1. What about partial V by partial T? Have you spotted? Yeah, that's over there. Oh, so you can just convert this. Oh yeah, it's actually working. It is in fact working. So if we just go term by term and then things cancel out, that would be nice. So you just cancel this stuff. Okay, and of course you have to put a negative, so just put a negative 1 over there. Cool. So that was awesome. So that's X equal to P, Y equal to T. Let's also go for, so P and V don't work, but maybe let's try Y equal to S. What about V and T? That probably would work. Yeah, let's try V and T. So X equal to V, Y equal to T. Right. So once again, this just dies. Then this thing is just, but this also dies. Fine. So you're gonna have a positive one now. So partial D by partial Y is this is just 1. So partial S by partial V at constant temperature is equal to partial P by partial X is V. Okay, that's Y over there. Sorry. Now this is 1. So Y is T. So this thing. Now where do we see that? this, and partial V at constant temperature. Oh, it's the reciprocal of that over there. So these two can be combined in some way, and okay, that just actually kind of kills both of these. Yeah, so that term is gone. Okay, so now we are left to this pressure volume thing. Pressure volume is slightly harder. I don't want to be dealing with that right now. What about entropy and volume? That is probably a good idea. Right. Okay, so y equal to entropy. So this term, it's gone. Okay, and this term is gone, so we get a normal equation. So it's partial T by partial V at constant entropy, that's equal to, so negative partial P by partial Y or something. Okay, so partial P by partial S at constant volume, I suppose. Okay, cool. I'm getting better at this stuff. I think so. So partial P by partial V, you don't have that, but you have the reciprocal of that. So you just need that to be multiplied with partial P by partial S, which you can get from here. So just take the reciprocals of these two and you get another negative one. So you just can kind of make another negative one, but then that kills off this thing. So it's just, of course this is also just gone. So just have one over there. So now the only thing remaining is to prove this. That is to say that partial S of partial V is equal to partial P by partial T at constant entropy. Okay, that is, how do we do that again? Oh, so pressure and entropy, right? So what is the pressure and entropy is? I should probably be doing the reverse of this. So partial T by partial P at constant entropy, that should be equal to partial V by partial S at constant pressure, and just remove these. And this is trivially true because that's just the next case, which is pressure and entropy. Yeah, so what do you get? This is just a partial P term. Okay, no, not this one, sorry. Oh yeah, okay, it is. And this is the partial V by partial S term, and this cancels because X equal to P. So yeah, and this is problematic. So this cancels because this, right? And so yeah, this is true, obviously. So 10th question is done. We have proved it, and the thing that we have used to prove this is this. So question number 10, essentially what we have proved is this relation, and this seems to be true for all sorts of what do we call it, systems. Here's no 11th question, sorry. Let's go to the 8th and 9th questions now. The 8th question is actually pretty big. Let's try the 9th question first, because 8th is something I want to do at the end. Okay, so 1 mole of an ideal van der Waals fluid is to be, so I think that's just an ideal gas, right? Yeah, it's taken by okay, van der Waals gas is also there, but is that what we're talking about? I don't think so. It's taken, is to be taken by an unspecified process from state T0 V0 to state TF VF. A second system is constrained to have a fixed volume, so its volume is fixed. Initial temperature is T2, let's call it T2 already, and its heat capacity is linear in the temperature. What is the maximum work that can be delivered to a reversible work source? What? Okay, let's try to visualize this. You have the gas, you have this constant volume thing, and you have some heat source. Sorry, you have some work source, and you want to deliver work to it, I guess. Okay, it's a reversible work source. I guess, okay, fine. So just some source that does this. Some work that can be delivered. Oh, okay, I get it. So these are at different temperatures, right? This is at T naught, and it's to be taken to TF, sure. And this guy, so this has a temperature which varies obviously. So if I kind of draw the PV diagram for our gas, this is at maybe at temperature T naught, some isotherm, and this is at some other temperature, right? Okay, and temperature varying linearly, some process that may be something like this, it follows that. So right, okay, just think about it. What we want is for the gas to, right, so we need to provide the gas heat obviously for it to make that sort of transition, right? So we know that an engine can only have maximum efficiency when um, you know like when all processes are reversible, right? Otherwise it cannot. So what we want is we kind of don't know if EF is larger or smaller actually. I suppose it's smaller. I mean, yeah, okay, TF must be somewhere in between T2 and T0, otherwise it wouldn't make sense. So I'm assuming that this is actually T0 and this is TF, and we are like going down. And while doing that, we're increasing the temperature of this guy, right? So the only way you can take away energy is through heat transfer to this system, which is at constant volume, can't do work or anything, right? Yeah, okay. The only work you can do is to this, work, what is called, it was called something, right? A work source, more like a work sink in this case, but whatever. So that's the only way you can do work. You can only take heat through this way. Your temperature will not change if you, okay, think about it. Work source, right? The only way you can take in heat is through that. And it has to reach this PF state. So the optimal scenario would be that all the heat was converted to work directly, right? Yeah, it has to reach the TF state. Okay, what is the maximum work that can be delivered? The work done on this, oh come on. So initially it's at T20. So what we want is that every transfer of heat should be reversible. That is to say that temperatures of your two bodies must be the same throughout, right? Like every time they interact. So first you must have the ideal gas go to the temperature T20, right? And whenever you leave, you will leave somewhere, but then you must always go back to the temperature, right? And you can sort of get work from the work, so but that's probably not the point. So just because later on removing that work is going to be hard. Then just get things for free, right? Yeah. Like you can't just convert all of that work to heat, because then you have to convert heat to work, which is not possible. Okay. Why am I saying heat? There is no such state property as heat, right? So what is it that we're doing? It's an adiabatic process, right? Yeah, it's an adiabatic process. It does not have any heat transfer, right? So the first process that we do is like we go from T0 to T20, and the only way we can do this is using some sort of an adiabat, right? Maybe something like that. So this thing is probably just this should not be high, maybe something like that. Okay, cool. So this thing is T2, so T20 is just the temperature of that body. Fine. Now once you have reached this state, you know that if you take in heat from this body, its heat will decrease obviously, so its energy will decrease, and its temperature is going to fall. Okay, so every time you have to take heat, you have to do it in a way such that the temperature is just that. Okay. Then can you ever go to the same temperature? No, because temperature is linked to the energy, so you would have to feed it energy, but the only way you can feed it energy is by doing work on the gas. So it's essentially an adiabatic. So as soon as you leave this guy's trajectory, so there's like two trajectories that you're following. One trajectory is of, I should just really just be doing a TV diagram and not a PV one, but fine. So this is a temperature, this is volume diagram. So you have the volume being constant, temperature changing, but we don't care about the volume of the gas being constant, right? So yeah, so this is some temperature T0. You were initially at T0 to T20. You were initially at T0. You had an adiabatic process, and how do I show adiabatic process over there? I don't know. I'm just gonna show it like a curvy thing, and then you reach this, right? Now you can only follow the process that there's only like one process, obviously, right? Sort of. The pressure can change though. Well, can the pressure? No, it can't. If T and V are fixed, it's fixed, right? So at that particular temperature, what pressure do you have? You could have any sort of volume really, but once you start decreasing this, your temperature should always change in a particular way. Okay, right. And after that you may sort of do an isothermal thing to change the volume, right? A reversible isotherm, completely doable, no problem with that. Work being done on the thing, cool, no problem with that, because it's reversible, so nothing much has been done, right? We just want the it's really complicated, isn't it? Going from higher temperature to a lower temperature, your volume should increase. Okay, it's an adiabatic expansion, so obviously your volume should increase. So initially you start off at smaller volume, you have a T0. Under the TV thing, I don't know what you get exactly, but like whatever, and then you do something, and then you reach at some point, this thing just is the temperature, fine, and then you follow the trajectory of this guy for some time, and then once again you just at that particular temperature just do something, so reach some pressure or whatever you want, and then you do this again for some time, and so on. You just keep doing this, and as such your volume is increasing, so you want to reach the maximum pressure in that way. Right. Oh, but you can just reach whatever pressure that you want, right? You can just increase your volume as much as no. The problem is you cannot do an isothermal thing because you see you cannot get heat. So the only kind of process that you can do is adiabatic if you are not following this guy's trajectory. And an adiabatic process is also not bad as such. what sort of process is it exactly that we're doing? This is a bit vague. You can get in heat from there and you can convert that. Sure. The outside cannot interact with the thing. Okay, cool. The temperature is being... Okay, so where is the heat sink? That's a good question. Where is the heat sink exactly? We're getting in heat, sure, but to what are you giving the heat? There is no constant temperature thing going on. The only real thing is that all of these are just... Oh, come on, just think about it. Your temperature change throughout that process, you know that... Oh, it shouldn't be that hard actually. Think about it. It doesn't matter what pressure you have. Right. So your energy flow is like this. From this constant volume system, you give it to the ideal gas, and then ideal gas gives it, in fact, everything that you have to this guy. Right. Some part of that heat also, in fact, goes to the ideal gas itself. Right. Well, that temperature is actually changing, right? Oh, so its entropy changes from so the system changes from T naught V naught to TF VF. Sure. Entropy of both of these guys change. Yes, that's correct. Okay, the entropy changed. What can you say? The TDS part. Yeah, you know that the integration of TQ upon T part, that was just this thing. Yeah, what's the work done? Oh god, this is so complicated. No, there's no easy process that just does this. You will have to find out the heat. You will have to find out everything. In fact, you'll figure out the energetics of this thing at least. Right. The total energy at the final state, that's fixed, right? Because you know that this will be at the same temperature as the... Or okay, yeah, I mean, I suppose it has to be the same temperature, right? You just like keep getting heat from this and converting it to work until that happens. Okay, this is very confusing though. So as soon as it disconnects from here, the only process you can do is adiabatic. Yes. So that does not have any sort of entropy change. Is the energy fixed? No, it's not. It's not. You can always like contract it a bit more. There's no problem. So you can certainly do adiabatic expansion as much as you want. Nothing problematic with that. Right. So what is your real constraint over there? The adiabatic expansion does not have any sort of energetic change, right? Yeah, that's sort of the thing. You want to maximize your work. Whatever temperature you have, but the temperature will change. So just keep the temperature as low as possible. That makes sense, right? Yeah. During the adiabatic process, keep the temperature as low as possible. Sure, but then why not just let the temperature go to 0 or something? Right? Just let your volume be that, right? Oh, you can't because the temperatures must be the same, in fact, for it to be able to do that. Okay, come on, think about it. Temperature may also increase. Okay, your temperature will have to be the same as that whenever you're taking in heat. Okay, so as soon as you disconnect, what happens? It was at some particular temperature when it was connected to this. Now you've disconnected. You can only do adiabatic process, and you want to reach the same temperature again. What choice do you have rather than to do some process and come back by the reversible path, and then say that, oh, we are at the same temperature. That's the only thing you can do. So that's almost as if you did nothing. So, oh, that kind of proves that these two must be in contact throughout, essentially. But otherwise, it's redundancy. Just that's the only thing. Oh, so the only real thing that you have to do is let T naught go to T20, and once it has gone to T20, follow this guy throughout. So first in adiabatic expansion, that does some work, fine. Then you must necessarily be in contact with this. There is no other way, right? So yeah, and then both of these will come to some final temperature, and after that, well, with that final temperature you can do some work. Once again, adiabatic expansion. The pressure, we do not know like how it's changing though for the outside scenario. It's doing work on something. We don't know what that something is exactly. Yeah, cool. So I guess that's the point. So the TV graph would be something like this, that you go from T naught to this temperature T20, then you do some procedure, and then once you have reached your final state, you actually have to stop, sort of, because you cannot let it go above, because then the only thing is like you want to go reverse. Yeah. Wait a second. No. What if like you get heat from there and then you convert that and then you actually do this back? That sort of cycle could really be useful, right? Right, so you just have to do positive work while you're doing it. The first, okay, I get it. You can just really just empty the whole tank from this guy. So you can let it reach as low temperature as possible, and then you can just gain all that back through an adiabat, right? And all of that is reversible engine, so no issue with that. That's not an engine, sure, that's certainly not an engine, but we were able to reach that. Okay, so now what is the maximum work that can be delivered to a reversible work source? So it's a 4-step procedure. First, we want to go from T naught to T2 naught using an adiabatic process. The work done in that scenario is just the change in energy, or the negative of that. So work done by the body as such. So just minus, and we are talking about some ideal gas, I guess. So minus and so just degree of freedom upon 2 and kb delta T, and that's just T final minus T naught, right? That's this energy change, and that's negative of that is the work done by the body. Okay, now once it has reached T20, now we just want it to H not be T2, H not be T final, it should be T20. Now that it has reached that, now we want to do work under this constraint that the heat capacity, so that the derivative of energy with respect to the temperature, that's just exactly equal to dt, right? Because that's the heat that we're giving. So the temperature should change in this way. Heat capacity is that whatever heat you give it should be such that, okay, yeah, I mean, makes sense. So your temperature should also change in that way. So essentially the heat input, right? Okay, that guy's temperature is decreasing, and so it produces this much of heat. Okay, the heat input to that, right? So your temperature is also just decreasing, right? Cool. So this should be dq upon negative dt in that case. Yeah, because the dq from that side is negative. So okay, it makes sense. Right. Yes, okay, so negative dq upon dt should be capital D times T. That's essentially our right. That's the equation that we should follow for for this whole process. So now what's dq? It's just de minus pdv, right? So plus pdv. This minus of de is just f by 2 and kb dt dt minus pdv. So minus is like, okay, plus, so plus pdv, but then again v is like can be written in a different way, so pdv can be written in a different way, I suppose. Okay, wait, whatever. Then upon dt, right? So this just cancels, just get dv upon dt essentially. That's equal to capital D times t. Amazing. What is dv by dt? So just have p naught v naught equal to p times, that's not good, so pressure times volume, that's equal to n kbt. That's probably what we should be using, and that gives us that as temperature changes, air pressure should change in that way. So everything's just volume and temperature. Cool. Wow, this is not good. Oh, we want a relation between v and t, that's why we were doing this. So from there you just actually substitute what p is in that case. So p is just that, and kb t upon v, right? Yes. And so you solve this, and then you get some equation for temperature, and so just go till that, and that's the thing. Okay, so then after that we actually kind of just keep going. In fact, you just keep going. So this whole thing you just keep doing it till tf equal to 0 or whatever. So it's just till 0, till like all of the energy has been consumed, and from there you do an whatever is it called, adiabatic contraction, and you reach there. I don't think this is how you draw the adiabatic contraction. It's probably just below that, right? This whole thing is reversible, and the thing is like even more of energy from this guy has been used, I suppose. Yeah. So yeah, the energetics say that the work done is the maximum in this case. Yeah, I guess. So it doesn't just reach T final, it actually reaches even below that. In fact, we don't even care like about this stuff really. We care about like the energy event that then was transferred from there. Yeah, that's about right. So essentially the energy that was transferred, like that was just the energy for the transition from T naught V naught to TF VF for the gas, and energy to go from temperature T2 naught to just 0 straight up, right? Yeah, that's what happened. That's the energetics. So that's just the work done, isn't it? Like just throw away the second law. You don't even have to deal with it, I suppose. I actually don't know. This is I'm unsure. I guess that's the thing. So okay, just integrate just integrate the whole thing in that case. So the dq thing is just cdt, but that's just capital D times t times dt, and so it's just integration of that, and it's going from 0 to t to 0. That's kind of the energy that was put into this block of whatever this thing was, just dt dt. So just like half t square is t20 squared, sort of. Just make it like reach absolute 0 or whatever, plus the work done from the gas. So it goes from T naught to TF. So just, and so this is like, okay, freedom by 2 and KB delta T, which is T naught minus TF, right? That's the energy lost, sort of, and this is the energy lost once again. So yeah, this is actually the maximum work that can be done, I suppose. I guess the whole thing was just show that there is a procedure that you can follow such that that work will be done. And I don't think any part of that was converted to whatever we call as heat. I think all of that just went to the surrounding. Oh, I don't want to delete that. Right? Because there is no way that you can do any sort of heat thing over there. I guess, yeah. Okay. And if it just so happens that it's not possible for us like to reach absolute zero for that particular body, well, I guess you can do a different thing in that case, right? Yeah. Never mind, just move on. So use Maxwell's. This is already done. So 9th is done, 10th is done. Let's go to the 8th question finally, the big one. Yeah. Liquid quartz, if it's cooled slowly, then it crystallizes at temperature Tm and releases latent heat L. Under more rapid cooling conditions, the liquid is supercooled and becomes glassy. Okay, so A is as both phases of quartz are almost incompressible, there is no work input, and change in internal energy satisfy this thing. Okay, use the extensivity condition to obtain the expression for mu in terms of E, T, S, and N. Fine. So you have this thing dE equal to TdS plus mu dN. So yeah, okay, the volume doesn't change all that much. So like we can just neglect the whole PdV term. Yeah. So when I find the expression for mu in terms of energy, temperature, and entropy and volume. So entropy and N, because volume is not there apparently. So I suppose we just do like E equal to how should I say this? The volume doesn't change obviously. So fine. So E is just Ts plus mu N. We can say that, I guess. Plus some like constant term? Not really, because it should be extensive. So I guess this is okay. So yeah, this is probably correct. Right. So if you like double the entropy, then the energy should. If you double the entropy and you double the N thing, then your energy should be doubled as well if your T and mu are the same. That's the intuition. So yeah, so just use the extensivity condition to obtain this expression, it seems. Another way of probably doing it is just this thing, partial E by partial, the N is changing, right? We can't really do that. So if N is changing, then we kind of have this thing that if S changes then N changes, then that's not good. It's not good. Okay, just think about it. E is, so we have this equation, right? E lambda S lambda N, that should just be lambda E of S and N, right? So just sort of differentiating this thing, you just get like dE is equal to, so dE upon d lambda, that's just equal to so we always know, like using chain rule, this can be just given as what the hell was I doing? Yeah, I was doing something, I kind of forgot, right? Yeah, just lambda dE upon okay, that's not cool. Something is really messed up. So like E is just partial E upon partial S, and then ds, and then plus partial E by partial N dN, right? Okay, so now if you sort of divide this by lambda, so like dE by d lambda, then this just becomes d by ds. Just think about it. That is lambda. It's just a very different thing, sort of. Wait, the equation that you will be getting by differentiating with respect to lambda, that would essentially just be just have partial E by partial s but evaluated at lambda s comma lambda n, right? Yeah, at times of obviously like ds, but now it's like ds upon d lambda. Okay, that's weird because this whole thing actually just changes, right? Oh wait, no, that's just the temperature obviously. So I mean that's like by definition it's a temperature. So it's the temperature at lambda. I mean that's constant. So extensivity, right? So just plus mu lambda n because it doesn't change. It stays the same, right? Yeah, I suppose. Okay, so that's equal to, so now if it, so with the right hand side, if you like differentiate this with lambda, then yeah, I just like get, it should be upon lambda, I think. You just get E of S and N. Interesting. Something is not correct about this, but I can't point my finger on what is correct about this. There should be some other term. But that's just the thing. Your energy is just that. It's just the derivative of entropy with respect to lambda. No, what the hell? This isn't right. This just isn't right. The derivative of that is entropy and then that times of. How does entropy change with? Oh no, okay, it's not that. It's not that. It's just S, because it shouldn't be ds by d lambda. It should be d lambda s upon d lambda. Right. So the equation that we want is, so differentiate this with respect to lambda. What do you get? You just get partial e by partial s evaluated at lambda s, and that times the derivative of lambda s with respect to lambda, which is just s. But you know that this thing is precisely just t and then plus some other term, this from this thing. So just like ts plus from there it's like mu n, I guess, and that's equal to this guy's derivative with respect to lambda, but that's just e. So you essentially get e equal to ts plus mu n from just extensivity. So that is the derivation. Cool. Then let's go for b. The heat capacity of crystalline quartz is approximately Cx. That of glassy quartz is this thing. Assuming that the third law of thermodynamics. So forget about that assuming thing. We just want to calculate the entropies of the two phases at temperatures T less than Tm. So Tm is once again the temperature when the liquid quartz crystallizes, right, and releases latent heat. So once again, we have crystalline quartz and glassy quartz, and they have some heat capacities, and we want to find the entropy of the two phases at different temperatures. So you want the entropy as a function of the temperature, I suppose, because the volume is sort of constant, right? So and then this is, you'll find some of that. Okay, fine. So we can just say that ds is equal to dq upon dt for some sort of reversal process, right? And since like these are constant volume things, there is no way to do work. So like the only way that you can actually add energy to this thing is by heat, and that just raises the temperature. This is like just a single variable that you can actually control, right? And of course the what is call it, the crystallization only happens at temperature Tm, right? Before that it's all quartz, or it's all what other thing was, so it's all crystalline quartz, or it's all glassy quartz. There is no in between. So anyway, ds is equal to dq upon, what is this, on t, and we integrate this thing. So just like the change in entropy before some any kind of transition really just is the integration of this thing. But then dq can be written as the heat capacity times dt. So for example, for the first guy, it's just alpha t cube upon t dt. So it's just alpha t square, right? But that's just alpha t cube by 3. So we can sort of just say that s, so it's like delta of that obviously. So like sx is just kind of just say that's alpha t cube by 3, assuming the third law that at t equal to 0 your entropy would be also 0, alright? And then similarly for sy, you can also just say that, so it's not y, it's g. So g is denoting the glassy quartz, and then x is the crystalline quartz. So for glassy quartz is just alpha, so beta, sorry, t square upon 2. So cool, you have the entropies of both of these guys. What do you want to do with it? Of course it's like up to some constant, right? So like plus something, but we just think that it's 0 because of the third law. So assume the third law, then you can calculate the entropies. Fine. And then that's okay, that's the B part. And the C is, at 0 temperature the local bonding structure is similar in glass and crystalline quartz, so that they have approximately the same internal energy. Okay, they have the same energy. Okay, calculate the internal energies of both phases at temperature some T less than Tm. Also apparently these are not so this liquid quartz, this glassy quartz and crystalline quartz are not two different phases. I mean, they are obviously, they're not two different like liquid or solid states, that sort of states. They're just different, like they're structurally different as such. Like their solid structure is different. I guess that's what is happening. Fine. Now at 0 temperature the local bonding structure is similar in glass and crystalline quartz, so that they have approximately the same internal energy. Calculate the internal energies of both phases at temperature T. Okay, so you've been given the heat capacity, and there's no work being done, so you can say like d equal to tds because n is obviously constant. So then, yeah, wow. So the dq thing is just like c dt, so just t c dt, right? It's sort of slightly different, yeah. So it's easy, just ex is integration of so we're just gonna say it's e naught plus integration from 0 to some temperature. And what do you have? You just have alpha t cube, that terms of t, so alpha t power 4 dt. So that's just e naught plus alpha t power 5, like okay, t power 5.5. Cool. And similarly you would have something for this guy. So e is, so for glassy quartz it's just e naught plus beta t power 4 upon 4. Cool. So you got the energies, you got the entropies. So far so good, making progress. So now what do we want to do with this? Next we want to use the condition of thermal equilibrium between the two phases to compute the equilibrium melting point in terms of alpha and beta. Okay, so when there's thermal equilibrium, okay, so essentially when you have melting and its equilibrium, what should be happening is that the mu of both of these should be the same, but we know that the mu is just given as, so more like n mu, that's given as e minus of, it should just be like one of these n things, but like whatever. So I'm just gonna say it's e minus ts, there's no pressure volume thing going on, so that thing upon n, right? So yeah, okay. So I guess there's a bit of a small thing that we should understand. So when it says energy E naught, it's probably talking about the same number of molecules, because if that's not the case, then yeah, this doesn't make sense. right? Same internal energy E naught, but that's like for the whole thing, right? Okay. Yeah, I mean, I don't think it should be a problem. I guess this is for a unit number of molecules as such. So let's just let that be the unit, right? So then what we want is like this essentially, that Ex minus T, that's equal to, so Tm obviously, and this is at M, and that's equal to Eg minus Ts. Yeah. And we want equilibrium at constant, but the pressure, does it really matter at this point? I don't know. But it should essentially be such that the entropy of the universe does not change. That's the way we usually do it. Yeah, that's probably the thing, right? So something enters, there's heat transfer, and that's the energy change, right? Yeah, I guess it's okay. It's okay, certainly, right? Yeah, your chemical potentials must be the same. That's probably the only real thing that you have. The the idea is that the entropy of the universe should not change. So like whatever heat that you take from the surrounding, that should be exactly equal to TdS for your whole system, right? So the heat that you take from the surrounding, well, that's just dE, the sum of them essentially, right? So at that particular temperature, your derivative of E with respect to temperature, that's sort of the thing. That's just the heat capacity, I guess. Yeah. So right, so it's just like alpha Tm power 3 plus beta Tm, right? That's kind of the amount of heat that you're taking. That should just be equal to your TdS sum, right? So it's just Tm times ds sum from there, right? Which is just dq by t in the first place. I mean, okay, that's kind of obvious, which is like true. Huh. Something is messed up, isn't it? What is the heat? Oh no, okay, this is not a process that we're not changing the temperature, we're changing the number of moles. Sorry. So now your d is not that. Now your d is like, since it's changing the number of moles, sorry, the number of particles and all that stuff, right? Like one particle is going from, it's converting to something else. Yeah. So what should you have? So temperature is not changing. Your overall entropy is sort of constant. This is messed up, isn't it? The entropy is in fact changing, right? Come on, just think about it. Change in the energy of these two. Yeah, so the difference of these two, not the sum, right? So beta t power 4 upon 4 minus alpha t power 5 upon 5. So if you go from X to glass, sorry, from crystalline to glassy, right? So that's the energy change. That's basically dq. That should be equal to T times ds. So the entropy changes once again. So for crystalline, essentially just have, so okay, we're going to glass, right? So just have beta t power 2 upon 2 minus alpha t cube upon 3. That's the thing. So it should be Tm everywhere, in fact, but we'll not do that later. Yeah, that's the thing. So then you just put that over there. So like it's t cube. Okay. It should be TdS change. Yes. Yes, it should be. The entropy certainly changed. Come on. Why are the dimensions not matching for some reason? Why is there a 2 and 3? That's a 4 and 5. What? No, something's wrong. But this should just be 3, I suppose. It should be 3 and 3, and this should be 4 and 4. Yes. It's CDT. right? And that's c by t dt, right? And c is given as alpha t cube, so it would be 4, right? Fine, it's okay, fine. This is actually 3, sorry. This is how it should be, right? So that is sort of messed up. This is not correct. We just have beta t power 3 upon 3 minus alpha t power 4 upon 4. That's the correct thing, sorry. So this is just a 1 by 3 minus 1 by 2 upon 1 by, more like 1 by 2 minus 1 by, that's better. This is 5, isn't it? Interesting. Okay, this should apparently not be happening, right? Yeah. So you're doing 1 by 5 minus 1 by 4. Well, this only makes sense if alpha is negative, but both alpha and beta are probably positive constants. So this should just not be happening. It's 2 and 3 over there. Oh, this is 3, sorry. This thing is 3, right? Yeah. That's why that's what's messed up. So just let that go over there. So just get like 1 by 2 minus 1 by 3, which is 1 by 6. So 1 by 6 beta t power 3, that's equal to, let that go over there. So just alpha, so 1 by 12, essentially 1 by 12 alpha t power 4, right? Just get t minimum is equal to 2 beta upon alpha. That's the thing, right? So that is the equation that you should be using. Not T minimum, it's T melting. T melting, there's no minimum. It's 2 beta upon alpha. The only minimum is 0 kelvins, which is not what we want to deal with. Compute the latent heat L in terms of alpha and beta. Releases heat L. Oh, so you want to compute. Alright, actually, like throughout this, we didn't actually use the latent heat, right? So it seems it's a property that we can compute directly. So we want to compute the latent heat under. Oh, alright, so at Tm, it's obviously changing. It's. Yeah. So what's the delta E essentially? It's the glass thing minus the crystalline solid thing. So it's just. So it changes from what to what again? I kind of don't know what it changes to. Okay, it becomes glassy. Where is the Tm thing given? So it crystallizes at temperature Tm, but these are both just different things. Okay, so it melts a little bit and right, yeah. So now you want to find the latent heat somehow. So it has to go to that particular state and then come back. Sure. Calculate internal energies. Fine. Under the condition of thermal equilibrium between the two, compute the equilibrium melting temperature in terms of alpha and beta. I guess. Okay. Liquid quartz closed. That requires. Melting temperature. Okay, I guess I misinterpreted this question a bit. It was not asking for equilibrium between these two phases. It was asking between some liquid phase that you have. So in that case, but we don't know the potential for the liquid, right? So now what? Okay, under rapid cooling conditions, the right, the glass thing becomes just glassy, right? But I guess under slow cooling conditions, which is like when the equilibrium is achieved, you probably get this thing, this, what is it called, the crystalline case. And so what should happen is that the crystalline thing is what we should be using for the equilibrium, most likely. It's like it's favorable, if that makes sense. But how could one thing be favorable? Like, that doesn't even make sense, right? Right, so under slow conditions, that's what happens, right? Okay, you want to calculate what Tm is, but how can I use thermal equilibrium between two phases to compute this? Probably because both are present. I guess that's the idea, like both of these are present during the process, like when it is crystallizing, and so that is to say there exists some equilibrium essentially. Okay, cool. It explicitly says use the condition of thermal equilibrium between the two phases to compute the equilibrium melting temperature, Tm, in terms of alpha and beta. So it was just correct, I guess. So Tm is certainly just 2 alpha upon beta, or whatever I wrote earlier. Then we want to compute the latent heat in terms of alpha and beta. Once again, both are to be used somehow. No, I don't understand. So at that point there is supposed to be equilibrium between all three of these phases, right? Yes. So yeah, and both of these are in equilibrium. Okay, so it does not matter whether you give the crystalline one more atom or the glassy one more atom. Both will lead us to the same change in entropy of the whole universe, which is like 0, obviously. Okay, so in that case, what do you want again? The condition of thermal equilibrium between two phases to compute the equilibrium melting temperature in terms of alpha and beta. I still don't get it exactly. The heat capacity at that point, they are not same. That's one thing we know for sure. Right. Yeah, okay, sure, we know that. What about it though? Like, one of these guys will just certainly have a bigger heat capacity, and it will just, like, grow more rapidly, sort of, or something like that. That's like kinetics, that's not thermodynamics that we are doing. So we don't want to be dealing with that, right? No, the thing is, the size of the phases, they don't really matter, do they? No, they don't. The size doesn't really matter, in fact. But the size does matter for the latent heat, right? This is like what part of it goes to crystalline, what part of it goes to that. But then to compute these parts, how would I be doing this though? Like, okay, just think about it though. I have seen this stuff before, phase diagrams and all that, but you are usually given stuff about the liquid as well. Over here we don't know anything about the liquid, so how am I supposed to calculate anything? The best I can do is just assume that the equilibrium is in fact between these two phases, and that doesn't make any sense. I'm just gonna say that that's the case. Okay, so I'm just gonna assume that the latent heat that we want is between the two phases that we are using. Of course that doesn't make sense, but we'll just do that. So then the latent heat would just be like the heat capacity of whichever one is actually like bigger, that thing. So I suppose Cg is bigger, so just beta times temperature is just 2 alpha upon beta. Okay, that minus Cx, so just alpha, and then T cubed, so 8 alpha cubed upon beta cubed. Essentially that just becomes like 2 alpha minus 8 alpha power 4 upon beta power 4, so beta cubed, right? Yeah, which can be done as like 2 alpha common, just 1 minus of 4 alpha power 3 upon beta power 3 something. Alpha has dimensions of temperature power -3. Now wait, okay, right, some dimensions that we have to put. Beta also has some dimensions. How are these even matching? It doesn't make any sense, doesn't it? It can't be just 2 alpha plus beta, that's probably wrong. Okay, how is that even the case? It can't just be 2 alpha plus beta, right? So 2 alpha upon beta, that doesn't make sense. That's temperature. We're saying alpha is, so alpha's dimensions are beta's dimension plus 1 temperature. It should be 2 temperature because of alpha T cubed. Something is extremely wrong again. Oh, that's cubed. I guess I messed up. This should be 5 and this should, oh I see, 2, so it's 4 upon 4 and this is 5 upon 5. Oh, that's slightly different. So now this is not, I just messed up a bit, nothing much. Yeah, so what you essentially have is beta t power 3 upon 3 minus alpha t power 5 upon 5, that's equal to temperature times this stuff. So beta t power 3 upon 2 minus alpha t power 5 upon 4, so that goes over there, just 1 upon 20. 1 upon 20 alpha t, that's equal, alpha t square in fact, it's equal to 1 by 6 beta, just that, right? So what you should be having is like Tm is not this stuff. Tm is, it's like this is 10, this is 3, so Tm is the square root of 10 by 3 beta by alpha. That's probably the better thing to do. Anyway, so now we get back to this E part. So you want to calculate latent heat. Okay, so it's just the heat capacity for glass, which is beta T. So it's just beta Tm, which is this stuff. So just square root of 10 by 3 minus the capacity for this thing for crystalline, which is alpha T cube. So just this thing cubed. So it's like 10 by 3 beta by alpha. I suppose, yeah, that's probably how I should be doing it. And then once again this some same stuff, so just this. So you can take some stuff constant, which is square root of 10 by 3 beta by alpha. And so now this just becomes beta minus 10 by 3 beta, which is negative. Interesting. So it's negative. Oh, that's actually very weird. In fact, I just negative 10 by 3 beta. That's not making very much of sense, but fine. So it's just minus 7/3 square root 10 by 3 thing beta square root of beta by alpha. That's the thing. It doesn't make sense, right? Yeah, the latent heat is apparently negative. How does this even make sense, right? So is the result in the previous part correct? If not, which steps are leading to this is most likely to be incorrect. We assumed that you require thermal equilibrium to do this, but in the E thing you are, so this is just really stupid, I think so, because latent heat L, you can't just calculate it like that. You can't just say it's the heat required to transfer from alpha to beta. It should be the heat required to transfer to alpha and beta from the liquid substance. So it doesn't make sense for it to be negative. I don't get what the point of this question is. It didn't give me anything about the liquid substance and just wants to ask like what's the latent heat. Yeah, this is just stupid. It is certainly just stupid, isn't it? Sure is. Fine. So I'll see you guys in the next video.